Alright, hello class. Today, in this video, we're going to be looking at the ratio test. And this is our first foray into tests that help us in things that either may be too difficult for the comparison tests or too difficult for the integral test. So as an example, if you had something like n over n plus 1, maybe n squared plus 1 raised to the n, something like this, where your entire thing's raised to the n, trying to set up a comparison test or like a integral test is going to be fairly difficult. Same with if you end up with a factorial. And I'll talk about in a second what those are. But if you end up with a factorial, I won't say we don't have ways to integrate that, but we don't have ways to integrate that would be worth our time, ultimately. So the ratio test is one of these first tests that actually give us a little more power when it comes to what types of series can we approach. Okay, and this is usually joined with the root test, which is similar. Okay, for this particular one, I'll just focus on the ratio test, and in the next video we'll talk about the root test and maybe have a bit of compare and contrast between the two. Alright, so here's what the ratio test says. So we're looking at a series, we'll just call it A, capital A, just a series of AKs. And we're going to let R be the limit as k goes to infinity of the absolute value of AK plus 1 all over AK. So this is why it's called the ratio test, because what we're doing is we're actually analyzing the ratio of adjacent terms or subsequent terms, right? We're comparing the k plus 1 term with the kth term and seeing how that, or where that goes, what that does. So you can imagine we are comparing the 10th term to the 9th term, or the 11th term to the 10th term, the 100th term to the 99th term. Okay, so here's what the test says. If if that limit exists and is less than 1, then A converges absolutely and thus just straight up converges. Okay, so it's a bit of a stronger condition, but we do have that A converges. Okay, if on the other hand R is positive, then A diverges. Okay. And unfortunately, if R is equal to 1, then the test is inconclusive, so we'd have to do something else instead. All right, now why does it work this way? Well, you may recognize that, or you may wonder, or you may not wonder, I don't know, why we may be using the same letter that we do for geometric series. And that's not by mistake, okay? We're using R because of the geometric series. So, I'm going to take a moment to kind of explain what's going on here. So, if the limit as k goes to infinity of the absolute value of, say, k plus 1 all over AK equals R, then that means past a certain point, okay, every AK plus 1 all over AK absolute value is approximately equal to R. Okay. So past a certain point, every ratio here is approximately this, which actually gives us that for past a certain point, I'm going to write this again, so past a certain point, right? It might be the 100th term, it might be the 10th term, it might be the millionth term. You know, that doesn't really matter. We just know that past a certain point, if I move this AK over, we have that the absolute value of AK plus 1 is approximately R times AK absolute value. Okay, so then from here, the series, the absolute value of AK, well, that's going to be absolute value of A1 plus absolute value of A2 plus absolute value of A3, on and on and on and on. All right, plus, then we'll get to the kth point. So let's let, here, I'll just do it like this. Absolute value AK plus absolute value AK plus 1, absolute value of AK plus 2, and so on and so on. Okay, so if K is the point where, let me call this statement here star. So if K is where the star statement starts to be true, I'll just say begins to be true, then past K will have, all right, so I'm going to write it like this. I'll have absolute value of AK plus absolute value of AK plus 1 plus absolute value of AK plus 2 plus absolute value of AK plus 3, absolute value of AK plus 4, and let's say absolute value of AK plus 5. Okay, so now I'm going to apply this star step. Now you might be wondering, well, what in the world do I mean by that? Well, AK I'm not going to change. But AK plus 1 I can say is approximately R times AK. Okay, and AK plus 2 is approximately R times AK plus 1. And so on and so forth. So AK plus 3 is approximately R times AK plus 2. And we'll have R times AK plus 3 plus R times AK plus 4. And remember, this goes on and on forever. Well, note here, I have an AK plus 1 again, which I could replace with R times AK. And then here, I have an AK plus 2. Well, I already know AK plus 2 can be rewritten as an R times AK plus 1. And then the AK plus 1 can be rewritten again as another R times AK. So we can reduce every one of these terms all the way back down to a bunch of R's and an AK. So let me write this down. We can reduce all of these down to absolute value AK. Okay, so when we do that, this is going to be approximately absolute value of AK plus R times absolute value AK, and I'm just going to say AK from now on. Then here I'll have two R's, so that will be plus R squared times AK. Here I had an R, an R, and an R, so I have R cubed AK. Hopefully by now you can see the pattern. Here we'll have an R to the 4th times AK plus R to the 5th times AK plus, and we can keep it going, R6 AK plus on and on and on. Then we will simply factor out the AK and then we'll have 1 plus R squared plus R cubed plus R to the 4th plus R to the 5th plus R to the 6th, on and on and on. And this is a geometric series. Okay, so what ends up happening is our absolute value series, and actually I'm going to use a, let me use a different letter here. Let me call this AN. Okay, so AN, it's going to be, I'm going to sum things up from n equals 1 to k minus 1. Okay, but then it's going to be AK times, then I have this geometric series, so it's going to be R to the n going from 0 to infinity. So I have this finite piece up to the point where that's approximately, and I guess I should really make this an approximately equal to. But at the end of the day, this isn't really a proof. This is just an explanation of like why this works. But so we have this finite thing. So this we don't have to worry about. That there's no convergence here. It's just some number. So we have some number plus a geometric series, and this geometric series will converge if R is less than 1. Okay, so that is why this works the way it does. So let me scroll back up just to the rule. Okay, and I'll show why 3 is true just with an example, but to get started, if that R is less than 1, then that's essentially what's happening. We can think of the series eventually becoming a geometric series. So in this case, A eventually becomes a geometric series. Okay, if this is true, well, it eventually becomes a, it's approximately a divergent geometric series. So A eventually, and I'll just say instead of becomes, behaves like a divergent geometric series. And if R is equal to 1, it's inconclusive. There's a lot of weirdness that could be happening in this case. So we'll look at this case as an example later. Okay, but before we do that, let's just look at some examples of how this works. One of the most common ways that we deal with this, or one of the most common situations where this becomes necessary, is when we see a factorial. Okay, so what is a factorial? Well, factorial, the notation is an exclamation point, and one way we can define it is basically recursively. So n factorial would be n times n minus 1 factorial, okay, where 0 factorial equals 1. And I'll explain this in just a second. Or, so this is recursively, or you can think n factorial is basically n, then times every natural number below it. So it'd be n times n minus 1 times n minus 2 times n minus 3 times, let's say 3, 2, 1. Okay? And similarly, we define 0 factorial to be 1. Now, you might wonder why 0 factorial is 1. So there are a couple of things where the factorial actually shows up. So the first example, we'll use calculus because that should be sort of close to our minds, right? Imagine that I take, let's take the first derivative of x. Okay, well that's 1. All right, then I want to take 2 derivatives of x squared. Right, 2 derivatives of x squared, so I'll take the first derivative and get 2x, and then I'll take the second derivative and get 2. Okay? Then I'll take the third derivative of x to the third. Well, that will be, all right, I'll take the first derivative, and I'll still need to take the second derivative of 3x squared. Then I'll take the next derivative. So the derivative of 3x squared, I'm going to bring the 2 down. So let me write it like this. 3 times 2 times x to the 1. And then when I take the next derivative, that just becomes a 1. So you get 3 times 2 times 1. Okay. Then I'll do the fourth derivative, or 4 derivatives of x to the fourth. Well, I'll take one derivative and get 4x cubed. We'll take another derivative and get 4 times 3 times x squared. I'm writing this deliberately. Then I'll take another derivative, and I'll still have to take one more derivative of 4 times 3 times 2 times x to the 1, which will be 4 times 3 times 2 times 1. And guess what? This is 1 factorial, right? It's the first derivative of x to the 1. This is 2 factorial, since it's 2 times 1. This is 3 factorial, and this is 4 factorial. So it turns out that in calculus, where we see the factorial pretty commonly is if I take n derivatives of x to the n, we'll get n factorial, which is n times n minus 1 times n minus 2 on up 3, 2, 1. Now, why is 0 factorial 0? Well, imagine if I follow this pattern. Let's say I take 0 derivatives of x to the 0. So 0 derivatives of x to the 0. Well, x to the 0 is 1. And taking 0 derivatives is basically just not doing anything, right? So this thing will just disappear, and then this thing will become 1. So that means 0 factorial must be 1. Okay, let me give you another explanation. Another way to think of the factorial is how many different ways are there to write in characters? So how many different ways are there to write, or let me say order, not three, I'm skipping ahead in my notes, sorry, to order n characters. Okay, so in other words, let's start with 1. So how many different ways are there to order a single character? A? Well, 1. Right? You can only basically just put down A. Okay? But if I have 2 characters, say A and B, well, I can order them as AB or BA. That's 2 ways to order. Okay? Now if I have 3 characters, A, B, C, well, all right, I have, of course, ABC. All right, I have ACB, I have BAC, I have BCA, CAB, and CBA. And I think that's all of them. ABC, ACB, BAC, BCA. Yeah. So we have 6 ways to order 3 characters. Well, 6 is 3 times 2 times 1, so that's 3 factorial. Okay, then if we have 4, A, B, C, and D, well, guess what? I'm not going to go through every single possibility, but there will be 4 factorial ways to order four characters. Okay, well that's 4 times 3 times 2 times 1, so that's going to end up being 24. Okay, so there are 24 different ways to order 4 characters. Now, here's where we get to 0 factorial, and why 0 factorial is 1. How many ways are there to order 0 characters? Well, there's one way. Not write anything at all. Okay? It's not 0 because that's not correct. Some would even argue there's an infinite different ways to not write anything, right? You could not write anything from the top or the bottom or whatever. That's an argument for a different day. But essentially, the one way is you don't write anything. You have a blank. I'm just using this line as a blank, but that's the one way to order or to write 0 characters. Okay, and some would argue there's infinite ways, but I don't want to get into that. There's one way. Okay, so that is a common question I get a lot is why is 0 factorial 1? It's because of this, what the factorial represents. It actually represents something, and that something wouldn't make any sense if we allowed 0 factorial to be 0. Okay, so let's now get into examples of how we use the ratio test. Specifically, a lot of times when we have the factorial, that's usually when we want to use it is when we see a factorial in the problem because the ratio test is perfect for factorials. And I'll show you why in the next example. Okay, so we'll start sort of slow here. We're going to look at the series k going from 1 to infinity of 10 to the k all over k factorial. All right, so the version of the factorial that we will want to use is this recursive one. this k plus 1 factorial is equal to k plus 1 times k factorial. Okay, this recursive version of it is what we're going to want to use. And that's because, remember what the ratio test asks us to look at. We want to look at this r, which is the limit as k goes to infinity, of the absolute value of ak plus 1 all over ak. Okay, now, like we did with the limit comparison test, I often go ahead and take the reciprocal of ak. Right, so I'm not doing a fraction over a fraction every single time. I just multiply by the reciprocal. That's usually how I end up doing it, just to speed up the process a little bit. But here we go. It's the limit as k goes to infinity of ak plus 1. So the absolute value of ak plus 1, well, I'm just going to replace all these k's with k plus 1. So this will be 10 to the k plus 1 all over k plus 1 factorial. All right, hopefully so far so good. Now I'm going to multiply by the reciprocal of just the ak term. So I'm just going to take this term, take its absolute value, and flip it around. All right, so this will be the limit as k goes to infinity. Now, all these things are positive, so I can actually drop the absolute value bars. A lot of these will be that way. A lot of times these things are just positive anyway, so we can drop them. All right, so I'm going to do the steps that will help us simplify this. So this recursive step, I'm going to rewrite this k plus 1 factorial as k plus 1 times k factorial. And this is something we'll also use a lot. Say 10 to the k plus 1, I can rewrite as 10 to the k times 10 to the 1. Okay, so this will also help us simplify what we're working with. Okay, so I'll have 10 to the k times 10 to the 1 all over k plus 1 times k factorial times k factorial all over 10 to the k. And now, thankfully, we get a lot of stuff that cancels, right? These 10 to the k's cancel, and these k factorials cancel. So now we're just left with the limit as k goes to infinity of 10 over k plus 1. All right, and here this is broken down really nicely. I have a constant over something going to infinity, so that's going to 0. So r equals 0, which is definitely less than 1. So A converges by the ratio test. All right. Unfortunately, this is one where you can't just say the RT because we'll have another RT with the root test in the next section. So we do have to go ahead and say which one we're talking about here. Okay, so this is in general how this will work. Things will cancel away, and hopefully you'll get down to something that, you know, is nice and you can take the limit of, and hopefully it will be less than 1 or greater than 1 so you can tell whether it converges or diverges. All right, let's look at another example. All right, let's ratchet up this difficulty a little bit. This next series we're going to look at is a series k going from 1 to infinity, negative 1 to the k times k to the k all over k factorial. All right, so your first instinct here might be to use the alternating series test because this is an alternating series. However, the terms here are not that easy to play with in determining this with the alternating series test. Okay, I'm not 100% sure that this is decreasing. I know they're all positive, but so I see factorial. So usually to me, factorial tells me ratio test. There might be a situation 1 out of like 100 where that won't be true, where you might want to use something else instead. But for my money, the ratio test is always a good option when you see a factorial. Okay, so we're going to set up our R, which is the limit as k goes to infinity of, I'll just write absolute value of ak plus 1. So let it match, say, bk plus 1 times the reciprocal of bk. So we're going to do the k plus 1 term and then the k term. Now, here's where the absolute values are going to come in. It's this negative 1 to the k. The absolute values are going to kill that, which is nice, so we don't have to deal with it anymore. All right, so I'm just going to write it out explicitly. It'll be negative 1 to the k plus 1 times k plus 1 raised to the k plus 1 all over k plus 1 factorial. All right, so there is our k plus 1 term. And then I'm just going to take the k term and flip it and then multiply. Okay, so it'll be k factorial all over negative 1 to the k times k to the k. All right, now what's nice is these things are positive, and these negative 1 to the k's, the absolute value is just going to get rid of those, right? So we can simplify this down now. I dropped the limit sign, so I'll just use arrows from now on. So this will be k plus 1 to the k plus 1 all over k plus 1 times k factorial. Okay, and actually, now that I'm thinking about it, let me split this up as k plus 1 to the k times k plus 1. Okay, then I'll just leave this guy pretty much alone. It'll be k factorial all over k to the k. All right, now the k plus 1s here cancel. The k factorials cancel. So what I'm left with is k plus 1 to the k all over k to the k. Now, you might be thinking right off the bat here that, well, this didn't really simplify anything, did it? It almost looks, well, maybe not as bad, but it still looks bad. Well, here's what we're going to do. We're going to use some algebra to simplify this. Okay, since both the top and the bottom are being raised to the k, I can say that this is k plus 1 all over k raised to the k. Right, and we're almost done. I'm going to split up this fraction. This is k over k plus 1 over k, so this actually becomes 1 plus 1 over k raised to the k. Now, does this look familiar? Hopefully it does. This 1 plus 1 over k raised to the k, that goes to e to the 1. Okay, so r equals e, and e is definitely greater than 1, so b diverges by the ratio test. All right, let's take a look at this series. C is equal to the series k going from 1 to infinity of negative 1 to the k plus 1 times k raised to the 2k all over k factorial times k factorial. Hey, so this one doesn't look very nice. However, we'll just take it a step at a time. Okay, it'll be the limit as k goes to infinity of, now I'm taking absolute values, so I'm just going to give you a hint here. You can skip some steps when you get to this point because you're taking the absolute value. This stuff here is positive, and we know the absolute value will get rid of that negative 1 stuff, so we can just kind of skip straight to, all right, let me do the k plus 1 step. So I'm going to replace every k with a k plus 1. So this k to the 2k will become k plus 1 to the 2 times k plus 1. Okay, yes, it is that fussy. I don't know if that's the best word, but it's definitely that messy. Okay, and then each one of these k's will be replaced with a k plus 1. So it'll be k plus 1 factorial times k plus 1 factorial. So here we have 2 factorials. So, you know, definitely want to use the ratio test there. Okay. Now I'm just going to multiply by taking the reciprocal of this. Again, I'm going to ignore that because remember we're taking the absolute value, so we can do that. And it's really just k factorial all over k to the 2k. All right, so we'll do some simplifications here. This is, if I distribute that 2, and that's what I'm going to want to do, if I distribute this 2, you'll get 2k plus 2 here. Okay, and so then I can simplify that to be k plus 1 to the 2k times k plus 1 squared. Then here, I'm going to do the normal factorial thing, k plus 1 times k factorial times k plus 1 times k factorial. All right, and so then up here I'll have a k factorial times k factorial all over k to the 2k. All right, so let's cancel what we can. These k factorials, of course, cancel nicely, and this k plus 1 squared cancels with these k plus 1s down here. Very nice. All right, so then next, let me write what we have. What we have left is a k plus 1 to the 2k all over k to the 2k. All right, and then like we did in the last one, this will be the limit as k goes to infinity of k plus 1 all over k to the 2k. And hopefully this looks a little familiar because that will be 1 plus 1 over k to the 2k. And that, if you remember back from the first section in this module, that's going to be e squared. That will definitely be greater than 1. So C diverges by the ratio test. All right, so that is sort of how these end up working. Let me do another example, and then I will show some examples of the inconclusive case. Okay, so here we have k squared plus 4 all over e to the k. All right, now notice there's no factorial here. So you may wonder why we would want to use the ratio test, and honestly, there may be other tests we could use, but looking at it, I don't really want to use the integral test. We might be able to set up a comparison test, but I think I'd rather just try the ratio test here. It seems the best fit. Mainly, it's because the other tests don't look like they'd be much fun to do. Okay, now, thankfully, these are all positive. So we'll look at R, which is the limit as k goes to infinity of the k plus 1 term. So we need to be careful here. This is k plus 1 all squared plus 4 all over e to the k plus 1 times, and then just the k term flipped over. Okay, now I will mention sometimes if you see a single something to the k with some other k stuff, the ratio test works really well there too. If you just have a something to the k, okay. If with other things with it, okay. That's just hopefully that helps. Anyway, this will be the limit as k goes to infinity of, I'm going to actually FOIL all this out, right? So that would be k squared plus 2k plus 1, which with the 4 will be plus 5, all over e to the k times e. And then I'll just leave this alone. Now, the e to the k's cancel. Nothing else does, though. Okay, don't get cancel happy here. These k squareds don't cancel. Okay, in fact, what we have is this. It's the limit as k goes to infinity of k squared plus 2k plus 5 all over e times k squared plus 4. Okay, now, you could also say distribute that e. Let me distribute that e. So it'll be e k squared plus 4e. Now, I'm taking the limit as k goes to infinity, and the powers of k are the same on the top and the bottom. The highest powers are both on the top and bottom. So this goes to the reciprocal of coefficients. So this will go to 1 over e. 1 over e is less than 1. So r is equal to 1 over e, which is less than 1. So d converges by the ratio test. All right, good. Now, let's take a look at the inconclusive case quickly, and then we'll be done. All right, so let's look at two p-series that we already know how they work. So this here, I, which is the series 1 over k squared, this is a convergent p-series. Whereas this guy, just 1 over k, that's the harmonic series, which is a divergent p-series. Now, if we were to use the ratio test on these, right, if we calculated our r, so for this one, we'd have the limit as k goes to infinity of the k plus 1 term times the k term flipped over. Well, nothing really cancels, and we get k over k plus 1. The limit as k goes to infinity, so that's just 1. So this is an r equals 1 case where h diverges. And you might think that's the end of the story. It kind of makes sense that r equals 1 would give us divergence because, remember, this started to behave like a geometric series, and if it behaves like a geometric series, doesn't that mean that if r is equal to 1, we'll get divergence? Well, this seems to suggest it. However, if we do the same thing here with our convergent p-series, we'll get the limit as k goes to infinity of 1 over k plus 1 all squared times the reciprocal k over 1, or k squared over 1, excuse me, which is the limit as k goes to infinity of k squared over k squared plus 2k plus 1. Well, the highest power of k is still on the top and the bottom. They match, so this goes to 1. So this is another r equals 1 case where the series converges. So this is where the problem lies. When we get 1, anything could be happening. Fair? Because we would get 1 for 1 over k squared and for 1 over k, and we know 1 over k diverges where 1 over k squared diverges or converges. So r equals 1 is an unknown, right? So that's basically what that means. That for the ratio test, r equals 1 could mean anything. The series could converge, it could diverge. All right, so that would mean that we'd need to use a different series test, right? Either the integral test or comparison test or something else. Okay. All right, so I think that is good enough for one video, definitely. Hopefully that'll get you rolling on the homework, and I will catch you all on the next ones. Cheers.